Hello, welcome to the last class of static force analysis of module 1. This is something dealing with what is called a static force analysis of quick return motion mechanisms. This topic was not there in the previous couple of schemes, therefore you may not find any question in the question paper, but almost all the books which cover this topic, they discuss this topic, static force analysis, and it is nothing different, the analysis. The given starting mechanism is different, otherwise all procedure remains exactly the same. Okay. I remind you that this is not a quick return motion mechanism class, but still I just mentioned what are the different types of quick return motion mechanisms. One is called as offset slider crank mechanism. A slider crank mechanism whose slider is offset, that also can work as a quick return motion mechanism. I hope you know what I mean by offset. The line of stroke does not pass through the crank center. Okay, if there is a gap between the crank center and line of the piston, line of action of the piston, that is line of stroke. Okay, and they don't coincide, in that case it is called as a offset slider crank mechanism, and it is basically slider crank mechanism, and hence I am not going to discuss this again under this, because static force analysis of slider crank mechanism, static force analysis of offset slider crank mechanism is the same thing what I would have discussed. Okay, no change, and therefore, so there is another mechanism, quick return motion mechanism, that is called as drag link mechanism. So what is drag link mechanism? It is basically a quick return motion mechanism. So how is it? It is basically a 4-bar mechanism. A 4-bar mechanism, and it is a Grashof chain satisfying the Grashof condition L plus S less than or equal to P plus Q, and in that mechanism, in that chain, if you fix the shortest link, then that mechanism is called as drag link mechanism. So therefore, static force analysis of a drag link mechanism is nothing but a 4-bar analysis, which we have done 4-bar mechanism. So it is exactly one and the same. And therefore, these are the ones what we need to discuss, what is called as crank and slotted lever quick return motion mechanism, and the other one is what is called as Whitworth mechanism. So Whitworth mechanism also has a slotted lever, slotted link. I don't call it as a lever. Lever is basically something which oscillates like this. This is called as a lever. A lever which does not undergo complete 360 degrees rotation, that link is called as lever. Okay, so we have slotted link in both mechanisms, in crank and slotted lever. Slotted link is a lever in this mechanism, and slotted link is in Whitworth mechanism is also a crank. I hope you understand the difference between crank and lever. Lever is this. The crank is complete, which undergoes complete 360 degrees pure rotation. That is called as a crank. Okay, a link of any mechanism which undergoes full 360 degrees rotation is known as crank. So any link which undergoes angular motion, but it is not 360 degrees angular motion, it is part of it, and anything less than 360 degrees we call it as lever. Okay, and that is also called as lever mechanism. Okay, then so whether our starting mechanism is crank and slotted lever or Whitworth mechanism, it doesn't matter. Okay, so now let me draw one mechanism, say crank and slotted lever mechanism, something like this. Okay, you have what is called as the frame. This is nothing but the frame. The frame is quite long in crank and slotted lever mechanism, and this frame is very short in Whitworth mechanism. That is the difference. Okay, so you have what's called as a crank. You have a crank. Okay, a crank. And then you have another link here, which is called as a lever. This is a lever. And you have here, okay, and you have a slider. and you have a turning pair. And then at the end of this lever, you have something what is called as another link, and you have a slider to which usually the shaper tool is attached. And this is the line of stroke of the shaping tool. Okay, then this is. Okay, this is the mechanism which we call it as a crank and slotted lever quick return motion mechanism. This is going to be a crank, and this link is what is called as a slotted link, and this will not undergo complete rotation, it will only move like this. That is why it is called as a lever. Okay, so now this portion I would like to highlight here. Okay, so a similar thing you have it in Whitworth also. Okay, please understand here I have, so if I number the links, say this is fixed link frame 1 and the crank number 2, and this is slider number 3, and this slotted link number 4, and say this is 5, and this is 6. Okay, this portion where you see link number 2 and the slider link number 3, and also the lever or link number 4. You have 3 links there. Okay, so you should not come to the conclusion that this is a turning pair which connects link 2, link 3 and link 4. It is not like that. Okay, in real sense, if I make it clear, okay, this slotted link is something like this. You have a slot in this, and this is the remaining portion of the link. And inside this slot, you have what is called as a slider. This slider will be moving. Okay, this is what is my link number 4, and this is link number 3. Between 3 and 4, what do you have? You have a sliding pair. Okay, and this slider is connected to the crank with the help of a turning pair. So this is your link number 2. This is your link number 3, and this is link number 4. Between 2 and 3 we have a turning pair. Between 3 and 4 we have a sliding pair. And link 2 and link 4, they are not connected at all. They are not connected at all. Please make sure. So many times in the diagram we draw like this, but the real construction is like this. Please understand that. Okay, here link 2 and link 4, they are not connected. Link 2 and link 3, you have a turning pair. Between link 3 and link 4, what do you have? You have a sliding pair. Okay, so here turning pair, here turning pair, here also, and here also. So this is how what we have, what's called as the quick return motion mechanism, and of the type what is called as crank and slotted lever quick return motion mechanism. Okay, so little later I shall also give you the dimensions. Say it is something like this. Say A, and this is being called as E, and the distance between A and E, this is given as 500 mm. So I shall be skipping the first step. What is that? Drawing the given mechanism to scale, what is called as configuration diagram. I am not going to draw it. That you are going to follow it. I shall straight away draw a freehand sketch and write down the dimensions. And the line of stroke of this and this distance is also given, and this is 500. And then this point is being called as B. Okay, so how do you draw? So first mark E, then using scale whatever, then you choose A. Okay, E and A, you can mark them as the frame, and then mark another 500 mm and then draw a horizontal line. Okay, then EB is given as a 200 mm, and this angle also is given. This angle is given as 70 degrees. So therefore, mark 70 degrees here and mirror this 200 mm and mark this point B. Point B is marked. Then join this B to A and extend it. and extended. This point is being called as C, and you have been given what is called as BC. BC is 400 mm. This is given. Then this point is being called as D. Then you also have been given. Then A is known, B is known, extend and then mark C. Then C is known, CD. CD is 300 mm. So with C as center, 300 mm as R, you cut this horizontal line and get the D. At D, you mark a slider and that's all. That's the mechanism. This is what is being called as the configuration diagram. So in addition, you also have been given, you are applying a force F which is equal to 3,500 newtons on link number what? This is 1, 2, 3, 4, this is 5 and this is 6. On link number 6, you have applied a force of 3,500. When you apply this, what happens? This will start moving towards left, and because of this, through this link also, link number 2 also will start rotating. So I don't know whether it rotates clockwise or anti-clockwise, it doesn't matter. Okay, so I don't want this link 2 to rotate, and therefore, how do I stop it? By applying a torque T2. So I have been asked to find out what is the value of T2 to keep the entire mechanism in equilibrium state. That is the statement of the problem. So these values may change, and the exact problem, the problem in the examination will remain same. Okay. So the same procedure, go through all the mechanism, all the links. Okay, link 2, link 3, link 4, link 5 and link 6, and identify where you can start. Okay, link 2, you have a torque and one force at this F12 and another force from link number 3, F32. So it is a 2 force and 1 torque. So if I take link number 3, okay, so there is one force from 2 and there is another force from 4. Okay, F4 3 and F2 3. Okay, so now I shall draw the free body diagram of link number 3. This is how it is, link number 3. This is the line. This line is the same as this. Okay, so now this is link number 3. What are the forces? There is one turning pair which is connecting through this. I have a force from 2 on 3. Okay, another force from 3 on 4. From 3 on 4. It is perpendicular, that I know. Okay, it is perpendicular. The force in case of sliding pair is perpendicular to the contact surface. So this is the contact, you have this and this is where you have the other link. So this is the contact surface and therefore it is perpendicular to this. So this is the line and this is the line of action of what is this? F from 4 acting on 3. F4 3. This is perpendicular to this line. This is nothing but this. So if this is F4 3, then you have one more force. You know that. What is that force? What is that force? F2 3. Because it is basically a 2 force member, the 2 forces must be equal, opposite and collinear. So therefore this is the free body diagram. Since it has only 2 forces, but I don't know much. I don't know F4 3 magnitude, direction, and hence I don't know F2 3 also. Okay, then let me come to link number 3. Oh, sorry, link number 4. This is link number 4. What I have drawn is FBD of link number 3. Okay, this is all I know now, right now. Okay. So now let me go to link number 4. Link number 4. This is from here A, B, C. Okay. So how many? So F14 at A. Then F34. Okay, at this point perpendicular. And another force F54, F54, force from link number 5 acting on this link. So therefore it is a 3 force member, F14, F34, F54, and therefore I don't know many of them, and therefore I shall not draw the free body diagram of link number 4 right now. Let me go to link number 5. Link number 5, how many forces are there? 1. From 4 acting on 5, F4, 5. And another one, from 6, from this slider acting on link number 5. They are the only 2 forces, and therefore the next free body diagram, what I would like to draw is FBD of link number 5. I shall make use of this. So I shall draw, okay. So whatever you can, when you draw this diagram to convention, you can measure this angle, etc. All that will help you to draw this link. This is link number 5, and this is what is called as C, and this is what is called as D. C, D. Okay, so what force? This is link number 5. And what force do I have here? I have a force which is called as F45. And what force do I have here? F65. These are the only 2 forces, therefore they have to be equal, opposite and collinear, and which makes us to know the line of action of F65 and also the line of action of F45. I don't know their directions as of now, but I know the line of actions. Okay, after this 5, let me go to what is called as free body diagram of link number 6, FBD of link number 6. Okay, so link number 6, this is off. Okay, now at the center, I have a turning pin. So through this, I am going to have a force from link 5 acting on 6. So I have a force, what is called as F56. F56 and F65, they have the same line of actions, as one of them is action, the other one is reaction, and therefore I know the line of action of F56 because I know the line of action of F65. How is this? This is same as along the line of this link number 50. So this is parallel to this. Okay, the next one, I have a force from link 1 acting on 6. What is the kind of pair between 1 and 6? It is a sliding pair and it has to be perpendicular, and therefore this force is what is called as F16. So apart from these 2, I also have an external force, what is called as 3500 newtons. This is what is F, 3500 newtons. And these are the only 3 forces. After that, link number 6 is in a equilibrium state. So therefore, now draw force polygon. For that you choose K. Okay. So probably after choosing scale, I leave it to you. 1 centimeter is equal to maybe 500 newtons, something like that. Then you start the point O. Then you will draw 7 centimeters if you choose that scale. If you choose something else, then the length of this line will be something different. Then this is OA. Then you can draw it F16. I don't know the direction, you may draw it on the other side also. Okay. Then the next one. Okay. So F56. So I shall draw it slightly, I don't know whether when I draw this. Okay. So I know at the tip of the second force, I have to draw the third force, but I don't know the tip of the second force. But I know the tip of the third force, where it is going to be. The tip of the third force is going to be here. Starting from here, draw a line parallel to this and draw a line like this. Okay, start, come back and put the direction. This is my starting point. This is my first force, that is here. Then the second force is like this, it is downwards. Then the third force is like this. Okay, what is this force? This is F16. What is this? This is F56. You know, you can call this as B. So BO multiplied by scale. Scale of your force diagram will give you what is called as F56. So F56 I know. it is in this direction. Please remember, I know its magnitude also now. I have found it out. Okay, so similarly, if you also require to know F16 is downwards. Okay, so therefore I know F16, this length multiplied by scale, that will give you the magnitude. Anyway, if I am interested in knowing only T2, then I may not require to know what is F16. No problem. I know F56, F56 and F65, they are exactly equal and opposite. F56 is upwards, F65 is downwards. And these are the only two forces, they have to be exactly equal and opposite. Therefore, F45 is like this. F45 is known, then I shall be knowing F54 also, but of course I have not drawn it. Please remember, I know this magnitude and direction, and I also know the magnitude and direction of F45. Okay, so now I shall go for, so now I know F5. Now I shall go to the free body diagram of link number 4. So the next one is FBD of link number 4. Okay, how is link number 4? Probably you can measure this angle beta something like this, and you know what is A, and draw this line. This is your A, and somewhere here B. You don't know the length between A and B, you can actually measure in your configuration diagram and you can come to know. And this is what is your C. Here you have a turning pair. Okay, B and A. Please remember, at B you don't have a turning pair. Okay, it is a connection between 3 and 4. Okay, so now let me start at C. At C you have a connection between 5 and 4. So from 5 on 4, that is F54. F54 and F45, they are equal, opposite, and have the same line of action. So therefore this is F45, you know its magnitude and also direction, and therefore you draw a line parallel to this, fix the direction, it is opposite to F45, and this force is F54, you know this. Please remember, F54 is known. Then at B, what you have? You have a connection between 3 and 4, link number 3 and 4, and from 3 on 4, that is F34. F34 is exactly equal and opposite and have the same line of action of F43. So F43 will be, that is F34. F34 is perpendicular to this link. Because the slider and this link, they have perpendicular contact surfaces like that. So this line of action indicates what is that? F34. So this is your F34, this is F54, and this is where what you have? You have F14. This is link number 4, and this is where you have connection with 1 from link 1 acting on link number 4, which I have no idea. So one force is F14, this is second force, this is third force, and these are the only 3 forces that are active. So what is the condition of equilibrium? One part of that says all the 3 forces must have a common point. Okay, this is one force, this is second force. Let me get the common point of these 2 forces by extending this line and also by extending this line. So this is the common point of F54 and F34. Join, this must be the common point of F14 also. In addition, I also know that F14 passes through this point. F14 passes through this point and also passes through this point, and therefore if you draw this, this is the line of action of F14. I know the line of action of F14, I know the line of action of F54, F34, and I know F54 completely, both magnitude and direction. So therefore, now go for what is called as force polygon. Okay, choose some scale. 1 centimeter is equal to. You choose a starting point, say O. Draw the first force. Which one you know? You know F54. So start here. and draw a line parallel to this in this direction, and this is what is F5, 4, and I call it as A. Then you draw what is called as the second force. I shall draw F1 force A. I shall draw F1 force, a line parallel to this. So why this side? I don't know. You don't have to draw it this side only. You can draw it the other side also. Keep the option on the other side. Okay, this is the second force. I don't know the tip of the second force, but I know where the third force is going to end. The third force is going to end at my starting point. Starting from here, draw a line parallel to this. Draw a line parallel to this. So this is your starting point. This is your F5, 4. This is your next force, which is F1, 4. And this is your next force. This is equal to what is called as F3, 4. You can call this as B. This is first, this is second, this is third. Now this length AB multiplied by the scale of this diagram will give you F1, 4. So BO multiplied by the scale of the diagram F3, 4. And therefore now F3, 4 is so many newtons that I know now. So now I also know what is the direction of F3, 4. F3, 4 is known to me. F5, 4 is like this. F3, 4 is like this. F1, 4 is like this. If I know F3, 4, I know F4, 3. F4, 3 is like this. F4, 3 is like this. Therefore, what do I know? I know F2, 3 is like this. I know its magnitude also. Please remember, I know the magnitude and direction of F2, 3. Now, very simple. The last one, as usual. Okay. What is called as free body diagram of link number 2. Okay. What is that? Link number 2 measures 70 degrees, etc. You draw that. This is your A, E. This is your B. This is your, it is subjected to what is called as a torque whose magnitude direction is not known. Okay. At B, what do you have? This is link number 2. You have a connection with 3. You have a force what is called as at the turning pair. This is F3, 2. And what do you have here? At E, you have a force what is called as F1, 2. F1, 2, F3, 2. Two forces and also a torque. So F3, 2 is same as F2, 3 in magnitude but opposite in direction. F2, 3 is like this. It is perpendicular to this. So therefore, this is same. And what is the direction? F2, 3 is like this, and therefore F3, 2 is like this. Exactly opposite. Okay, if F3, 2 is like this, how is F1, 2? Parallel to that. Parallel to this. This is how F1, 2. If F3, 2 is like this, F1, 2 is like this. So you know F3, 2 magnitude also, please remember. Then find out what is called as, say if I call it as X, the perpendicular distance between the two. Okay? And then F3, 2 multiplied by X. F3, 2 multiplied by X is equal to the magnitude of the torque T. It is magnitude, not direction. Please remember. It's only the magnitude. F3, 2 and F1, 2, they form a couple in anti-clockwise direction. So the torque, what you have to apply must be in clockwise direction, so that there won't be any thing which is called as motion, and therefore it will remain in equilibrium state. And this is how. And T2, the direction of T2 is so many Newton, millimeter, and what is the direction? It is in the clockwise direction. This is the answer. Okay, I have only demonstrated the procedure, and even if your starting mechanism is Whitworth mechanism, and the procedure remains exactly the same, and hence I wish you to complete this, and I am not going to solve any problem on this, and if you get any problem you can practice it. Okay, so with this I declare that this topic is over, but I shall be very happy to answer your doubts, queries, anything, anytime. Okay, I welcome all those things. So when we meet next time, we shall go to module number 4. Okay, module number 4 and start a topic on vibrations. Okay, good day.